I know. So you're wondering what happens. It's all very well and good if the pivots are non-zero. And I know it's been just a joy to see that happen. But it may be that they're zero sometimes. And so we can deal with this beautifully. We'll deal with it kind of basically to start with, and then there'll be a more and more complete picture as things arise. In fact, we're completely happy about this. I think it's sometimes laid out that it's a problem or a disaster or a breakdown, but actually it's fine, right? So it's a very meaningful kind of thing. Okay, so let's lay out a couple of examples. So given this equation, this is going to be a short thing. We're just going to do two 2x2 systems. All right, so we've got these characters. All right, so there's row 1 and row 2. And let's put it into augmented matrix form because we love, that's very nice and tidy. We should be on top of that. We're always still really just playing around with equations, but this is the equivalent. So if we look at either of these, you can see that the x side of the thing is really just a multiple, right? So there's a -1 factor there. And if you think about that, right, you multiply that second equation by -1, you've got -x1 plus x2, right, across here, and then -5. These two equations then don't work, they're parallel. So this is just sort of by inspection. We wouldn't see this for a much more complicated thing with many, many equations, but so we can see something bad is going to happen. So let's see how it manifests. So we do the right thing. A nice tilde, yes, a little bit of flourish there. Row 2 prime, so we're trying to introduce a 0 here. We're trying to make a little upper triangular matrix. It's 2x2, there's only one entry to mess with. So it's always the new row 2 is the old one minus something times, in this case, row 1, because we're working on column 1. This is, as usual, this is L21, right? 2 is for the row that's being affected, row 1 is the one that's doing it. And on the bottom, I should have, it's always like this, on the bottom will be the first pivot. It's the pivot corresponding to the row that's doing the work, if you like. Okay, so that's a -1. Right, first pivot is always just sitting there as long as it's not 0. -1. And we have a +1 in here. Right, so you have to be, they're always -1s, +1s. So there's a +1 there. Okay? Right, so that's good. So let's see what happens. We know what happens, but let's see what happens. We are only changing, so this system is equivalent to this other system. It's not equal to. That's, again, this means has same solutions as. Same solutions as. This big tilde thing. Right, so we're not changing the first row, but we're basically adding, if these minuses cancel out, we're adding the first row to the second row. So that's easy, 0, 0, 6. Right, so this is a case where there's a 0 pivot. Pivot, and we say a pivot is missing. There's nothing to grab hold of, right? Pivoting, like in a sport or something, there's a point at which you can turn around. We can't do that. We couldn't use some multiple of this 0 to get rid of that 1, for example, right? We'd like to do that. And if it was a bigger matrix, we'd like to be able to use this pivot in the second column to wipe out all the other numbers, eliminate them. Okay, so it's bad, and it's bad because there's a 6 here, because if we go back out to the equations, we have, so row 2 now, again, dropping the prime, we don't keep primes, is really 0x1 plus 0x2 equals 6, or 0 equals 6. Not true. So there's no solution. So what that means is there's no solution. There's no solution. And these two equations, they ships in the night, right? They don't hit each other. They're parallel. That's the line version. Let's look at so the column picture. We should do that. The column picture is that, let's get the right thing. So this is -1, 1, and then plus x2 times 1 minus 1 equals 1, 5. That's what we're trying to do. And if we draw that picture, right, so 1, 5 is up here. This is x1. Sorry. That's important. The column picture is in y space, which we'll get to later on, y2. So this is b. Let's call this b, right? This is our b vector. This is 1, 5. Yep. And we're trying to add some multiple of -1, 1, and some multiple of 1, minus 1 to get that. And so, but -1, 1 is pointing out in this direction. Nope. -1, 1 is pointing out in this direction. This is vector A, this is vector B, and so that's a 1, that's a -1. This is, and this is -1, and this is 1. This is A2, this is A1. There's no way, so we can't add multiples of these guys, right? So all we can do if we add multiples of these guys to each other is trace out, and what I'll do, we can only trace out this line here. We can only get to points on that line, right? So, so there's no solution in this case. If B was a point on this line, we could do it, and there would be infinitely many ways to do it. So we'll come to that in a second. So hopefully that makes sense. So we'll say that this is there's a term we need to add here, and I guess I should have. Let me put it back at the top. So our menu. So singular systems. So this is a singular system. So sort of an archaic kind of term. So singular means odd or peculiar, right? Or as in rather individual. So sort of a singular chap, for example. So this so this is a example of a singular system. And this means there's no, so it's a system that doesn't have unique solutions. It doesn't have a single solution. So no unique solutions. And it may have 0 or infinitely many. Right, we're really going to understand this very well. One thing else that I want to say here is this gray line here, right, this thing. So that's a line in 2 dimensions. So we'll see that later on it's a subspace, right? So that the possible places that B can live, such that there's a solution, is a subspace. And we will call it column space. There's going to be a row space. There's going to be a null space. And there's going to be the rather curious left null space. But that's good. And you'll find out why you want to have a small left null space as a person. All right. Okay. So my left null space is small and yours is a form of abuse. All right, let's see. So, okay, so that sort of thing can happen again in a bigger matrix. You see this sort of thing. So you just sort of stop. There's no solution in this case. We could, however, have something like, let's say, different example. Right, so there's no way to make this. So then we'll call this example 1, and this is example 2. Let's go straight to the column. Well, I won't do it. I'll just give you I'll do the same format. Minus x1 plus x2, 2x1 minus 2x2 equals minus 2, and this one is equal to 1. So you can see that if you multiply this by the row 1 by minus 2, and of course it's much more complicated potentially. Row 1 by, what's up with that? Row 1, sorry. So this is row 1, this is row 2. If you multiply row 1 by minus 2, you get row 2. So they're the same equation, actually the same equation. So let's just see how that works out. Again, 3 by 3s, more complicated things, 4 by 4s, larger things. It will happen in more intricate ways, but this is just an intro story. And there's a very important thing I want to introduce here. So the augmented matrix version, boom, boom, great. 1 minus 2. It's always good practice to do these things. So same formalism as ever. So it's row 2 prime. It's going to be the old row 2 minus some multiple of row 1. Just want to do this over and over. I've jumped. Okay. Okay, so at this point the recording kind of went bad in terms of audio. I think I fixed up the technical issue there. And so I'm just going to cut this piece in and go over the last section here, which is just on the right. So just this stuff, right? So it's already written. I'm just going to talk through the story here. Okay, so where we were, we have these two equations. Just this is what we're given. And we can see they're multiples of each other, right? So the second one is just minus 2 times the first, or the first one is minus a half times the second. So they're the same lines, they're the same equations, so we anticipate getting infinitely many solutions. These equations are both true for an infinite number of points. Good. All right, but we're going to go through our method mechanically. And we set up our augmented matrix. So just put the rows into an augmented matrix. So there's a, it might not be obvious sometimes when you look at this, right? There's a minus 1 times x1, that's what this is. There's a plus 1 times x2, and that's that 1. And there's more obviously a 2 here and a minus 2, 2, minus 2, and then 1 and minus 2. So we've encoded this structure into the augmented matrix. Right? And again, this is really a x times b, right? That's what this, ax equals b. That's exactly what this is encoding. Fine. And we're trying to get to ux equals c. We're trying to make an upper triangular matrix. So we'll be able to do that. So again, the standard structural, everything in blue here, right, we always put down. We're modifying the second row, and we're going to use the first row to do it. Right, so 2, 2, that's what we're modifying. Row 2, the new row 2 is the old row 2 minus some multiple of row 1. Right, good. And we've thought about this and we said, well, look, if we've got a pivot, a number there's some substance there, it's a minus 1, we can divide row 1 by that number. That then gives us a 1 here. And if we multiply by 2, then we can subtract this new multiply of row 1 from row 2, and it will get rid of the piece that was here, right? So this 2 is going to get eliminated. These are the words we use, which seems a little extreme. Okay, now if we do that, multiplying, so we're really, if you look at this is really 2, we're adding 2 of the first row to the second row. So let's do that, and if you just look at this equation, then of course we end up with zeros along the bottom. Same equation. So this is what we would call a singular matrix. It has a missing pivot. It's an example of a singular matrix. What we say missing, this is 0 here. So there's no substance there. There's nothing we can use to then say do other kinds of row reduction. That's why we talk about it being missing. There's nothing to pivot from. This is now in the form ux equals c. So far we've seen triangular matrices, I think so far. And then this is in the form where actually you can still make your little stair step. It just goes across further. And we call this an echelon form, staircase form. Okay, so singular is going to have deeper meanings as we go along. Everything is connected. Everything keeps getting connected as we go further into the course. We stop here. We've made our triangular matrix, or our upper triangular matrix. Even though it's not a triangle, it's still upper triangle, which for a 2 by 2 means there's a 0 here, right? There can be any numbers here, but that's an upper triangular matrix. Back substitution is how we solve from now on, right? So we pull everything out. We've of course still got equation 1 usually, and unless you do row swaps, row 1 will always be row 1. We just modify the rest of them. It doesn't matter how big the system is. And the bottom row says 0 times x1 plus 0 times x2 equals 0. That's fine, 0 equals 0. So this is telling us something in the sense that there's a missing pivot, but we can just ignore this equation, right? This equation it doesn't tell us anything new about mathematics, right? So, okay, so I'm going to introduce a couple of terms which generally we sort of talk about later, but I think it's good to talk about them now. So pivot variables. So the pivot variables are any variable, we're looking down the columns, that are associated with a healthy pivot. So there was this nice pivot here, right, -1. That's the first pivot. There's no pivot here. So we have x1 we're going to call a pivot variable. Perhaps, right, so it's associated with a pivot. More strongly is what happens to anything that's not a pivot, and it's a free variable, right? So we're going to have these two terms, pivot variables and free variables. When we're talking about the x1, x2, x3 up to xn, they will eventually always be divided into pivot and free variable, right? So remember, this is simultaneous equations. Turns out there's a triangle times triangle story, and there are all these extra things we can start to think about. Pivot and free variable, very, very important. And when we talk about free, what we mean is free in the sense of we allow it to be anything, right? So it's a independent variable. And then the pivot variable is dependent upon it. It's like freedom fries, not French fries, which are actually Belgian fries. Okay, Mel Gibson kind of freedom. That's what we've got here. Mel Gibson. All right, so what we say is x2 can be, we've got a few R's in this course. This R1 means the real numbers. R2 means the plane, R by R. So that's going to mean real numbers. Right, we have these with the 1 at the top. So we let that variable be anything, and now we've got x1 is depending on x2, so we're going to rewrite the only equation we have. I'm just swapping it around here, right? So this is from here, minus x1 equals 1 minus x2. And then just a tiny bit more algebra, right? There's nothing here. We just multiply by -1. So x1 is whatever this free variable is minus 1. So for free variable 17, x1 is 16. And again, x2 can be anything you like. So you let that dial up and down, and then that will give you x1. This next, so again, very formalized ways we do this, right? So this is a very formalized thing for row operations. Here's another important step. When we've got to our solution, and we have free variables and pivot variables, even if we don't have free variables, we'll still use this approach. We write down x, we just say x, right, the vector x, and then we say it's equal to x1, x2, which in principle goes down to xn. We just write the x's out, and then replace all of the pivot variables with their expressions in terms of the free variables. So for us, x1 is x2 minus x1. So we put that in here, leave the free variables as they are because we're not changing them. Boom, so it's just the same. And now we've got an expression that just depends on x2. And we're going to break it into a simpler expression or a more understandable expression, hopefully, which is this. So it's going to be whatever free variables you have times constant vectors plus some constant vector on the sitting. So in general, it'll be all of the free variables will have a vector associated with them, a constant one, which is just made out of fixed numbers, plus some fixed offset vector, if you like, right? So fixed here. And then this is dialable, and that we can make x2 go up and down. And this is the 1, 1 vector, right? So it's pointing here. If this is the normal x1, x2 plane, right? We can dial anything like this, and we're going to add it to this vector here, -1, 0. Groovy. I know you're excited. You're excited. Okay, so... And then this is an important thing to add. You always have to put this where x2 is an element of the real numbers. It could be x2 and x7, right? You list all the free variables. Good. So let's make sure we understand that this is working, right? There's x2 minus 1. That's really 1 times x2 minus 1. And then on the bottom, there's an x2, which is just, again, 1 times x2 plus 0. So that's how we can break this into this expression here, right? There's x2 times 1, 1, and then this is an offset vector here. I'll leave that there. Okay, so that's the solution. And because there aren't enough pivots, right? There's a singular matrix here. We have this possibility that we can get an infinite number of solutions. What we did before was, let me say this, before we had no solutions, right? Again, pivot is missing, but there were no solutions because we got 0 equals 6, and that's badness. Here we have our zero pivot problem didn't matter, and everything worked out. And the geometric interpretation, again, for 2x2s is that in the first case, we have two lines that are parallel, they never touch each other. In the second case, they are on top of each other. Column picture, very important. Let's just finish with that. For this second problem, let's go, well, sorry for the zooming. Let's go back to what this was. So first column, -1, 2. Second column is 1, -2. And we want multiples of those columns to give us 1, -2. And so that's the column picture. Here it is. So some constant times the A1 vector, right? So the first column of the matrix A, some variable times the second column, and they have to combine, right? So the thing we've done over and over and is built into all of this is I hat and j hat. Some multiple of I hat, some multiple of j hat gives you any point in space. And we're generalizing from that. We always have the anchor of I hat and j hat, if you like. Now, so what does that look like? Well, let's draw out, so our A1 is here, right? So it's -1 + 2. Our A2 is over here, so it's 1 and then -2. So they go in opposite directions, right? The A1 is equal to -A2. And then if we take any constant times one of them plus any number times the other and add them together, all we can do is trace out points on this line, right? We can just go back and forth, back and forth. We can't ever go off that line. We don't have enough freedom to move off that line. So if B is out here, for this example, there's no solution. If B is on the line, there are infinitely many ways we can get there because we can go further and come back, or back over this way and come back, and we can slide that around. So that's exactly how this works in this case. So that's an important interpretation. So if you look at this, most points in this, and it's very important, this is a y1, y2 space. Most points in this space you can't get to. Most vectors you can't make. It's only a very special, small, right? It's just one line within the space that you can get to. And last thing to say is these vectors, right? These are A's columns. So A's vectors, column vectors, they live in this other space. And we're going to write this y1, y2, y3. So that will all come later on. This is good. So things can go bad, but we're happy with bad. In fact, this example seems there's no solution. Later on, what we'll do is we'll get the best solution, right? So that's very important, our best approximation. So we don't give up because we are hardy matrixologists. All right, good. Carry on.